In this video, I'm gonna be explaining how we use Siamese representation learning for relation extraction. This paper in 2023, and unsupervised relation extraction aims at discovering underlying relations between named entity pairs from open domain plain text without prior information on relational distribution. Using unsupervised relation extraction models utilizing contrastive learning, which attract positive samples and repulse negative samples to promote better separation, have got decent effect. However, fine-tuned relational semantic in relationship makes spurious negative samples, so damaging the inherent hierarchical structure and hindering performance. To tackle this problem, we propose Siamese representation learning for unsupervised relation extraction, a novel framework to simply leverage positive pairs through representation learning, possessing the capability to effectively optimize relation representation of instances and retain hierarchical information in relational feature space. But why is unsupervised relation extraction promising? Existing relation extraction methods which are restricted to specific relation types have achieved good performance. Nevertheless, with the rapid emergence of large domain-specific corpora and new relation types, these methods face many challenges. On the one hand, manually establishing and maintaining the ever-growing relation requires, because each day you have a new relation, so you should update your database, so all the algorithms should be updated accordingly. So it's promising and receive widespread concern, since it does not require prior information on relation distribution. First, we don't know the distribution, what will happen in future, so we don't know the prior, to reduce the reliance on labeled data and can discover new relation types. But contrastive learning is just an enemy of hierarchical relations. The core idea of instance-wise contrastive learning is to pull together the representation within positive instances while pushing apart negative ones. However, negative examples are commonly sampled from the batch or training data at random due to lack of ground truth annotations. In relation extraction, the relational semantic tend to be more fine-grained and based on a potential hierarchical structure. For example, per state province of residence or per countries of residence, and so these are in one benchmark dataset. They share the same parent semantic on all of them are people residence, and which means that they belong to the same cluster, semantic cluster from hierarchical perspective. So naturally, instances may have highly similar semantics in a batch, but contrastive learning pushes these representations apart as long as they are from different original instances, regardless of their semantic similarities. So the architecture is like this. First, we give the input to these deep transformer, and then we have these views. We have different views. And so this is very similar to BYOL architecture, and they have nonlinear mapping, but BYOL has a projection in both sides as well, and this side has something, but this side is missing the other one, so that the architecture becomes asymmetric. But in this paper, they also add semantic clustering. So they are also talking about nearest neighbors of each sample and semantic clustering loss as well. So they attempt to propose a Siamese network architecture only using positive pairs like BYOL or SimSiam, we only use positive pairs, not negative pairs, to eliminate adverse effect of spurious negative samples. Siamese networks are able to learn similarity metrics of relations from labeled data of predefined relations, and then transfer the relational knowledge to identify novel relations in unlabeled data. Therefore, we intend to use Siamese architecture to construct positive pairs and learn relation representation in unsupervised setting. For the most part, owing to lack of labeled data, network is easy to collapse. We have two kinds of collapse: collapse to a point, collapse to a subspace. To avoid this, we introduce entity type which provide a strong inductive bias for relation extraction as prior information. So we aim at developing a joint model that leverages the beneficial properties of self-supervised learning to improve the unsupervised relation extraction. The encoder module instances as input, which are composed of natural language sentences and entity pairs, and then employs the pre-trained model to output entity level features, pair sets H and H prime for all instances. And the learning module is structured as Siamese architecture and takes pair sets respectively as input. And we use similarity representation loss, which measures the cosine similarity of positive pairs to enforce the relational feature of instances that have similar semantics. But in the clustering module, we're mining nearest neighbors of each sample in relational feature space to learn discriminative representation under semantic clustering laws and can yield better clustering performance. So we add entity types as prior information in head and tail. So start and end of head and tail. This is for head, this is for tail. So this is how they are using the entities as well. So we get the token embedding, and theta here is just the learner parameter in the encoder. And we use the embeddings with the position of H sub I and position head and tail as outputs. So we concatenate head and tail as it is standard in the literature to get HI. Then we follow data augmentation using in the classic purpose SimCSE to construct positive pairs. Specifically, we only feed the same input to the encoder twice. So the way that they are using this augmentation is just dropout mask that I've explained in a different paper, which plays on fully connected layers as well as attention probabilities, and we can obtain, because in NLPs it's difficult to obtain augmentations, we have to use these dropout mask. But in computer vision, you can use many rotation, transformation. There are many ways to do augmentation. But in NLP, it's so challenging. So that's why many people just use dropout mask as a kind of augmentation. Of course, the different methods could be designed. And we use Siamese network, which can naturally introduce inductive biases for modeling invariances. And we use this multi-layer perceptron G to map feature pairs to G sub I and G sub I prime. And phi here is just the learning parameter. And here we use stop gradient, just like BYOL or SimSiam architecture. And the architecture is non-symmetric. So given a training set, the relation encoder, instance encoder can obtain two augmented relation features for each input instances. So we minimize negative cosine similarity between positive pairs. And so this is just a stop gradient of the other path. We usually in the literature called this the online path or online network, and this path is called the target. In the literature, they always say target and online. And then we minimize the negative cosine similarity for a mini batch of n instances. One of the main obstacles for our model is difficult to learn a discriminative representation without negative samples. We assume that in an excellent relational feature space, each example with their nearest neighbor have similar relational semantic and belong to the same relation. So we propose semantic clustering to learn discriminative relation representation and conduct clustering. So like adaptive clustering, we aim to learn a clustering function. This is our clustering function, which is just parameterized by a neural network. And the neural network classifies each instance and its mind neighbors, because these are the mind neighbors, together with the learning parameter sigma. The function terminates in a softmax function to perform a soft assignment over the clusters, and the probability of an instance x sub I being assigned to cluster C is phi sigma C. So the first term imposes phi to make consistent prediction for each instance and its neighboring samples. However, the dot product will be maximal when the predictions are one-hot and assigned to the same cluster. To avoid phi sigma from assigning all samples to a single cluster, we introduce this entropy term. So this is the entropy term, phi prime, which spreads the prediction uniformly across the center. So it's also related to uniformity, because we have two measures for validation of all these to see if we are collapsing or not. One of them is uniformity, the other one is alignment, which I have explained both of them in a different lecture. Uniformity, it means that if we have a hypersphere, we want to spread into different parts of this space. And the alignment is just focusing on just a particular subset of the subspace. And so we introduce relational semantic clustering module to further refine the semantic and enable them to be more discriminative. So eta is just a loss coefficient, and so it combines the Siamese representation and the relational clustering, because this is the clustering loss and the other one is relation extraction using that contrastive paradigm.